Hey, Professor.
Hey,
Yeah, so it's a religious holiday today, so I might be leaving a little early. Is that
no
fine?
problem. No problem. Thanks for letting me know.
Yeah.
What holidays today?
It's Eid al-Adha. Yeah.
What's it for? What does it mean?
So it's like the celebration of our of like the Muslims completing their required pilgrimage.
So let me start the recording, and before we begin, I'll show you a little research paper that I found that I thought was super interesting. So this is a young student that just graduated from Berkeley, and he got a job at University of Chicago, which is kind of like one of the great schools that's out there for economics. And so he is from LA, I think, actually, Chris Campos. And he was a super interesting person. He was in the military before he went to graduate school, and just a really nice person. And what he studies is in LA, they started opening, they put different schools, they started this thing called zones of choice. So if you didn't like the school you were assigned to go on based on your neighborhood, if you were in a zone of choice, you could choose other schools in your zone. And so what he does is he looks to see what happens to achievement in these places when the zones of choice are implemented, compared to places where a zone of choice isn't implemented. So this figure up here I'm going to put it in the middle so it's easy to see, is what happens to achievement when the zone of choice is implemented. And what's kind of cool here is that you can see that before it's implemented, there's nothing there. I don't know if you can see my mouse, but that before the zone of everything before the vertical dashed line is before the zone of choice was implemented. And you can see that's just flat. And what that means is that the zone of choice schools are trending in a similar way to the non-zone of choice schools eventually. And then after the zone of choice is implemented, what you see is the zone of choice schools start doing much better than they would have if they hadn't become zone of choice schools. So this is a 0.2 standard deviation effect. That's like, that's pretty big. I'm trying to think of a way to explain it. Like the typical rich-poor gap between students in their test scores is about 0.6 standard deviations. So simply by by opening zone of choice, you are able to close about a third of the rich-poor gap, which is pretty large, pretty amazing. And then this is their test scores. And then maybe you think, test scores aren't really what we care about. We care about other things. This is for college enrollment. So you see that the college enrollment of the students attending these schools goes up significantly. So that means that it's not just their test scores going up. There's sort of real lasting differences in the outcomes of these kids. So I thought that was a really interesting paper. The other interesting thing is that the effect isn't from kids changing schools and going to a better school. It's actually from bad schools becoming better when the zone of choice, because there's a zone of choice. They know that if they don't get better, they'll lose more students. So they really start to hustle and they improve the quality of their education. It was a really important kind of topic just for understanding intergenerational mobility. If you're worried about inequality or stagnation among low-income people, this is one of the really kind of promising avenues to address it. Okay. Any questions from anything? Any questions from earlier? Any questions from yesterday or earlier last week? Okay, sounds good. So let me also, before we start, I just want to do a little bit of coaching on the test. So tomorrow, first of all, tomorrow's a quiz. So just make sure you take the quiz. I gave you the topics in that email that I sent yesterday. So there are no surprises on the quiz, and you have 15 minutes to take a 5-question quiz, and you know basically every topic that's on the quiz. So that should be just easy points. On the test, this is how I would study, and I've heard from students that this is just like kind of helpful advice, is I would start going through the slides, starting at the beginning. And when there's an example, I would take a notebook, a fresh notebook, and I would write out the example and do the work of the example, which is nice because you can usually check the work either against my slides or against your notes or against the recordings of the lectures, and just make sure that you know how to do those. And then when there is a definition or concept or anything like that, I would write it down in the notebook. And then if that definition or concept or whatever it is, the formula doesn't make sense completely to you, if you don't feel like you understand it, then I would go to the text and I would read about that. And once I had read enough that I felt like I'd understood it, I would write the explanation to myself in the notebook. So then what you have after a couple days is you have a study guide of everything that's likely to be on the test. And I'm basically writing the exam from our slides, and that's really it. So there won't be anything much more complicated or difficult than kind of the examples that we do. There's a few questions will be based on kind of understanding what we're doing at a deep level, but for the most part, you can get 90% of the points by just understanding the slide deck at a pretty superficial level, in my opinion. And that really is the best way to learn, is to read and to write and to explain it to explain it to yourself, and then to review and review and review. And that's kind of all of the little pieces of the class can start connecting to one another when you do that. Okay, so what we were talking about yesterday is this cool tool that we have, which is that we can start including multiple variables in regression. And so sometimes we call this controlling. So we could try to estimate the relationship between education and wages while controlling for experience. So why do we want to control for experience? Well, if experience is correlated with education and also with wages, if we ignore experience in the regression, this coefficient will be biased. So basically, if there are variables that affect the outcome variable and are correlated to the X that we're interested in, here is education, then the coefficient on education will be biased if we don't include a control for experience. So we'll go into that deeper later. So basically, what we're going to have is that when we estimate these equations, the interpretation of the regression changes slightly. So now what we have, for instance, in this one is that for a 1-year increase in education, your wages tend to increase by $1.50, holding constant your experience. So we're going to imagine that experience won't change, doesn't change. So it's as if we're comparing among people with the same experience who had different levels of education. That's kind of the intuitive way, is finding people that have the same level of experience at different levels of education, or if we're interested in the effect of experience, finding people with the same education that had different levels of experience, and measuring the relationship among people that have the same education or experience. Okay. So the fun thing is that we can actually just keep adding variables until we're out of variables, basically. Actually, until we're out of data. So you can't have more variables in a regression than you have observations. And that's just because If you have more unknowns, which are your betas, then you have data points. You literally just can't estimate all of them. Okay, so how do we interpret beta 1? Beta 1, and I'm going to go to our effect language, is the effect, just because it's simpler, the effect of education on wages holding constant. Experience and sex. Okay, so here we have, in this regression, we've got education, experience, and male, which is basically, we're just going to have a control for sex. So female will be 0 and male will be 1. And that's just the same as controlling for differences in sex. So it could be, for instance, I don't know, males tend to have a different experience or education profile than women. We can control for male so that we're making sure that the beta on education isn't reflecting differences in education between men and women. So by controlling for it, we basically shut down that tag. How do we interpret beta 2? Beta 2 is the effect. Remember, these effects are in quotations. It's not exactly the effect. It's the effect of experience on wages holding constant education and sex. And then how do we interpret beta 3? See, this is a great example. It's the effect, but not really, of sex, of male, on wages. Holding constant education and experience. So there's a kind of a cottage industry of lawyers, and when they'll sue for racial discrimination or for sex discrimination in an employer, and actually what they're going to run is a regression kind of like this one. So they'll run a regression where they've got, say that there was anti-male discrimination alleged at some company, Microsoft or something like that. The lawyer would basically say, we need all of your salary information, Microsoft, and we need all of your, for all of the workers, not just for the worker that's suing us, but we need it for all of your workers. And you need to let us know their education, their experience, their occupation, their number of years in the business, whether they've had outside offers, their sex, etc. And then the lawyer would hire an economist like me, and we would run a regression just like this, except we'd have lots more controls, plus beta 4, x4, plus beta 5, x5. So these might be, this is like occupation. This is, whether they had an outside offer, what their outside offer was. So an outside offer is if you get a job offer from another company, the place that has you right now will often match it so they can try to keep you. So it could be that men or women are more likely to get outside offers. If they're maybe women are more likely to be looking for an outside offer, so they're more likely to get an outside offer. You wouldn't want to say that men are being unfairly paid just because women were going out and getting an outside offer. And then what we'll do is basically look at this coefficient on male, and if this is significant and negative, it means that people, men, or have the same amount of education and experience, occupation, outside offers as a woman are being paid less than a woman with the exact same education, experience, outside offer, occupation, etc. So it can be kind of it's a useful thing. They actually find that usually when they do these big regressions and they control for industry and occupation and education experience, that the gender gap almost vanishes. It's less than a percentage point. So it's very, very small, very small gender gap in the economy at large. And among young people, there tends to be a reverse gender gap where women tend to earn slightly more than young men. Young women tend to earn slightly more than young men. Okay, so the coefficients beta 1, 2, and 3 are not only interesting in their own right, but they become more meaningful when we're able to fix other things, when we're able to control for other things. So this is, when we look at this, we say, wow, we really do have kind of a good reason to believe that this is something like the effect of education, because we're controlling for all these other things that we've put into the regression. So it's not due to these other things that the education is associated with different wages. Okay, any questions here? Let me just pause. This is a good time to pause. Let's see. Kimberly, Katrina, Ibrahim, Esmeralda, Devin, Derek, Danielson, Cameron. Anything? Any questions there? Thumbs up. Who was thumbing up me? Who is it? Who is thumbing up? I'm just kidding. I don't care. I'm just interested because it just says thumbs up. It doesn't say by whom. Okay, no questions so far. My water. Oh, there it is. Okay, so say we had some data and it looked like this. We've got wages on the y-axis. We've got experience on the x-axis here. And when we draw a straight line through the data like this, what we find is it doesn't fit the data that well. So the data are above the line here in the middle and below the line on the edges. So we say that doesn't really fit the data very well. What can we do about that? Well, there's a multivariate regression that we can perform that will help solve this. So all we do is we include, so say we were interested in the relationship, obviously, between wages and experience. We can include a term which is experience squared. And then why is this multivariate? Because we have two parameters and we have two variables. We have experience and we have experience squared that are in our model. And that is going to allow this line to curve instead of be straight. So it's going to allow us to basically hit all of these points. So this is just an important little explanation of what the parameters mean. So beta 1 captures the initial slope of wages with respect to experience where y equals 0 or x equals 0, and beta 2 captures whether that slope is becoming more or less steep as experience changes. So in this example right here, what sign do we think beta 1 has? Is beta 1 positive, negative, or 0? What do you think? So beta 1, I think you're on the right track for the next bit, Leana. Beta 1, if we look at the slope at x equals 0, the slope of this line will be positive. So beta 1 is likely to be positive, okay? In this example. Leana, do you want to explain why what you're thinking? Because I think you were just early.
Oh, I thought that you were talking about the other side of the graph. That's why it's the negative slope.
No, it's good. So the beta 2 is the curvature parameter. So it'll be the sine of this will be the sine of the second derivative. Okay. So do you know the sine of beta 2?
Would that be constant? So it's
Say again.
constant? That would be more like a constant. It's kind of like a flat looking line.
Okay. So because are you saying because it flattens out here?
Yeah, or I mean, second derivative. So it's more like it's like the. I mean, if it's the first one is a slope, then the second derivative it's not really a slope anymore. So
That's right. It's
uh,
not a slope. It's how the slope changes as experience changes. So I'll help you out a little bit. The slope is going to start out positive over here, like we said, and it's going to get more and more negative. As you can see, it's going to first, the positive value will flatten out, and then it will eventually start to turn negative. So the second derivative is actually negative because the derivative is becoming more negative as experience increases. Okay. So beta 1 will be positive. Why is it positive? It's positive because the slope where x equals 0 is positive. Remember, we had this line that was like, the dots are like this. So at 0, the slope is positive, and therefore, this is a little sign that says, means therefore beta 1 is greater than 0. Beta 1 will be positive. What sign does beta 2 have in our example? Beta 2 will be negative. Why is beta 2 negative? It's because the second derivative of these points will be negative. And what that means, when the second derivative is negative, it just means that as x increases, the slope decreases. As x increases, slope decreases. Therefore, beta 2 is less than 0. So this is not a calculus class, but there's just a little bit of kind of intuitive calc that comes with it. So we can talk more about this. The other thing, so say you were trying to find the optimum, the maximum of a function, how would you would have to do two things. First, you take the first order condition and you set it equal to 0. You take the first order derivative and you set it equal to 0. The second thing you do is you test to make sure the second derivative is negative. Okay. Second derivative is negative, then you know that there's an optimum. If the second derivative is positive, and you would have a curve like this, so there won't be a maximum, there will only be a minimum. This is if you've taken a calc course before, you've seen something like this. Okay. Yes, that's a great idea. Okay, so let's take a second derivative here. I think we're going to see one on the next, in 2 slides, but we'll do it right here. This actually is a great idea. Okay, so we're going to take the derivative of wage with respect to experience is going to be, okay, so the derivative of beta of this term with respect to experience is 0. The derivative of this term with respect to experience is beta 1. And the derivative of this term with respect to experience is, we're going to take down the exponent, 2 times, I'm going to get rid of this little times because it just gets messy, beta 2 times experience plus the derivative of this term with respect to experience is 0. So it's just the derivative is beta 1 plus 2 beta 2 experience. So what do we know from this? We know that the slope, so remember, whenever we take the derivative of an equation, what we're learning is the slope at every given point. Is that the slope of this function is dependent on experience. As experience changes, the slope changes. Okay, so if instead we had, in our normal world, or not the normal world, but in the world before this example, we had our equations were something like this. Wage equals beta naught plus beta 1 times experience. So the derivative here is just beta 1. And all that means is that the slope is constant. So what does a line with a constant slope look like? A straight line. If the line isn't straight, then the first derivative is, then the derivative is changing as x changes. So anything that is not a straight line will have a changing derivative. The derivative will change as x changes. Okay, so we're going to do a little example together. Okay. So what's the predicted wage for someone with 2 years of experience? Okay, this is going to be pretty good. We're going to say wage is equal to 7 plus 1 times 2 plus minus 0.05 times 2 squared. Okay, so 0.05 times 2 squared times 4 is 0.2. Okay, so what we get is 7 plus 2 minus 0.2. That's going to be equal to like 8.8. Is that what anyone else got? Yeah, is that what anyone else got? Okay, awesome. So then what's the predicted wage for someone with 10 years of experience? We're going to say 7 plus 1 times 10, so that'll be 10, plus minus 0.05 times 100. So this is going to be 5. So we're going to get 7 plus 10 is 17 minus 5 is 12. You guys get 12? Okay, awesome. Know that the difference in wages per year of experience is less than $1 times 8 years of experience. Note that the difference in the wages per year of experience is less than $1 times 8 years. Okay, so yeah, so remember in this term, it says that basically we'll get $1 extra for every year of experience. Here, what we find when we compare this, remember we started with 2 years of experience and we're getting an additional 8 years. So if it was just based on this first term, we'd have 8 additional dollars, but we don't. We're not being paid almost $16. We're being paid just an additional $3 or so. So what it means is that we're not getting a full dollar for every additional year of experience. We're getting $1 minus 5 cents per year, per squared year of experience. Okay. So I think actually this is exactly the data. This is exactly the line that the estimate that we would find if we estimated these data points. You can just see as we're getting to 11, 12, 13, 14 years of experience, the marginal increase on your wage is not that great. Okay. Okay, so let's go back and do this. Just touch on something that we did a little bit ago, which was take the derivative of our regression with respect to experience. This was our equation. We're going to take the derivative. I showed you how we get this derivative. It's just that the derivative of this with respect to experience is beta 1, and the derivative of this with respect to experience is 2 times beta 2 times experience. And all that means is that the slope varies with experience. That's all it means. So in our example, what's the slope when experience equals 2? If I give you this question, all we would have to do is plug 2 into our derivative equation here. So we would have beta 1 plus 2 beta 2 times 2, because we're just plugging in 2 to this experience right here. So we'll get beta 1 plus 4 beta 2. But you know what I think that they want us to do is to do this for the example right here. So let me get that data. 1 minus 0.05. 1. So the beta 1 is 1 minus 2 times 0.05 times experience. Just clean this up a little bit. So this is our derivative equation. So we can say 1 minus 2 times 0.05 times 2. It's going to be 1 minus 0.2. Because 0.05 times 2, oh no, I'm sorry, that's wrong. No, that's right, is 0.1, and 2 times 0.1 is 0.2. So the derivative here is 0.8. What does that mean? It means that at 2 years of experience, each year of additional experience will increase your wages by $0.8. In our example, what is the slope when experience equals 10? It's 1 minus 2 times 0.05 times 10. 1 minus. So this will be 0.5 times 2 is 1. That means it's 0. That means at 10 years of experience, you don't get any additional your wages don't rise as your experience rises. So your wages are rising as your experience rises early in your career, but not late in your career. Okay. Did anyone get these two alongside me, or did I goof the math anywhere? Ned, Cameron, Dennison. Also, yeah, any questions here? Okay, math is okay. Good. No questions here? Okay, sounds good. Okay, suppose that we're interested in estimating the effect of years of education on wages, and we want to include experience so that we're holding it fixed. Since we know that the relationship between wages and experience has a curved shape, it makes sense actually for us to include experience and experience squared in our regression equation. So say if we know that experience has a curved relationship with wages, if we're trying to understand education, it makes sense for us to model experience in the way that we know experience is related to the outcome variable. So just to say, when we know something about how variables respond to each other, it's useful to just use the model that we think is right. Okay. So this is probably not that clarifying. Initially, we had a two-dimensional grid where we'd have points, or here might be X and Y, and we'd have points like this. And then we would draw a line through those points. When we have two X variables rather than one, it takes the shape of a three-dimensional space where the regression isn't a line, but a plane. And the plane goes through, minimizes the distance between the plane itself and the data points in that plane. So here you can see that basically this is the plane that describes the regression line. And these points are the data points. And then these distances here are the distance between each data point and the predicted plane that we're estimating with our regression. So if that's helpful, that's great. And if it's not, it's not super, not a lot is based upon it. Okay, so last time in our last deck, when we were deriving ordinary least squares, when we were deriving where our betas come from for regression, what we did is we remember we're minimizing. Minimizing the sum of the squared errors. And we notice that the error is just the yi minus the predicted y, where the predicted y is equal to beta naught plus beta 1 hat x1. And actually it can have as many betas in it as we can fit into the data set. So here, instead of minimizing, we basically, this right here that we're minimizing now is just this. We're subtracting the yi from the new predicted value. And we will be able to take the first order conditions of that, set them equal to 0 to find what the beta naught, the beta 1, the beta 2 ought to be. Okay, set them all equal to 0. We'll have 3 equations. Notice now we have 3 unknowns rather than 2 unknowns because we've got a beta naught, beta 1, and beta 2, where before we only had beta naught and beta 1. But because we have 3 equations now, we can solve for the beta 2 as well. So basically as many parameters that we put in there, we'll take a derivative with respect to each of those parameters. That gives us a new first order condition to use to solve for what each parameter ought to be to minimize the distance between the plane or the hyperplane or the line that we're estimating and the data points themselves. So I'm not going to make you go through all this because it gets really annoying super fast. But you'll just it's just helpful to know that this is where our regressions are coming from. So we did this before actually in the last deck, and nothing is different here except that we have more variables in the background. So when we are trying to calculate the R squared, we're still going to calculate the sum of the errors from between the data and the predicted plane. That there are sum of squared residuals. And then the difference between the true y and the mean of y is essentially just the variance in y. So that's the sum of squared variance, or sum of total, I always forget this. What's the word? Okay. Sum of squares total, or the total sum of squares. And then we divide SSR by SST and subtract that from 1 to calculate the R squared. So in a test, I might ask you to calculate the SSR, or I might give you the SSR and SST and ask you to calculate the R squared. Those are two kind of realistic things that I could ask you. Okay, so this is really important. When we add additional variables, it always improves the R squared. So you can never find a variable that when you include it, when you add it to a regression, it will reduce the R squared of that regression. It will at minimum just keep the R squared the same, but usually it will be increasing it slightly. And what that means is that economists actually don't use R squared that much, because it can explain more than is really there. Like R squared, you can make it look like the R squared is explaining a third of the variation in the data, when really you've just put in a bunch of variables that don't relate to the outcome variable. But we are choosing, so our betas are choosing, our regressions choose the betas that maximize the increase in the R squared. The R squared is kind of, you can think of it as like a hungry monster. It will keep eating new variables and getting bigger and bigger, even if the variables are garbage. So you can literally put in noise. You can make variables that are just random. They're not obviously related to wages. And if you keep putting in more random variables, your R squared will get bigger and bigger. So that's kind of one of the reasons we don't use R squared that much. But it is fun, especially if you have a variable, if you have two variables and you think, oh, wow, how much of one variable can we explain? You get something large and they seem unrelated. That can be really interesting. Okay. So suppose that we regress a student's college GPA on his or her high school GPA and their ACT score. Did you guys take ACT or SAT?
SAT.
SAT, cool. ACT. So you can kind of take either and both. Lots of you took both. You know, on the incoming class, do they have to take the SAT or the ACT, or can they submit them if they take it? Okay, so you can submit it, but you don't have to submit it. Is that right? Okay. There's maybe I'll show you that next time. There's a really interesting study that the UC that some faculty did that basically shows that SAT is really good for predicting which disadvantaged students will do well in college. And so there are some interesting costs associated with getting rid of the SAT. So suppose that we know that two students have a predicted college GPA of 3.5, and one student had an ACT score of 20, and student two had an ACT score of 25. What high school GPA did they have? This is a great question. So first, the math's not super complicated, but it explains something that will be kind of interesting, I think. We'll do the math and then I'll show you the insight. So we have 2 kids and their predicted college GPA is 3.5. We have 1 kid whose high school GPA we don't know, but we know his SAT score was 20.05 times 20. And here we have 3.5. I got to put this in a different place so I can do the math. And I'll put it in a different color. 3.5. .05 times 25. So right away, who do you think has the higher GPA? Is it student 1 up here with the blue, or student 2 down here with the green? Who has the higher GPA, do you think? Any guesses? Cameron, Noah, Derek, Esmeralda, Kimberly, Leanna, Neb. The top has a higher GPA. Okay, so we have a vote for top. No other guesses? Okay, you guys, you're fun. Okay, so let's just do the math. So we have a vote for above and a vote for below. Another vote for below. Okay. Wish I could just do a poll. Wouldn't that be fun? Oh, poll. I can do poll. Okay. Add a question. This way it will be private. Add a question. Is this working? I don't know if you can see. Oh dear. Yes. GPA. 1, 2. I'm gonna launch this out to you guys. Okay, let's take it for a minute if that's okay. Can you see me? Can you hear me? Can't hear anybody, so I don't know. Can't see anybody. Can you guys see the poll?
Yeah, we can.
Okay, sorry, I've never done that before, so I don't know. Okay, we've got 10 votes. Can we get okay, can we get 2 more votes? Okay, so I'll end the poll. That's true, we got 80%. Okay, so I don't know if you can see this, but we basically have, let me share my screen so I can. So this is a pretty cool. So we have 33%, the class is split into thirds. So we have 33% of you guys, 33% think this guy will have a larger GPA. And 67% think this guy has higher GPA. Okay. So can one of you guys tell me why it is that you think this guy will have the higher GPA?
Actually, the first one has higher GPA. I was trying to plugging in like 4 GPA, 4.0 for the GPA, and the first one actually I got 3.5, but the second one I got 3.75. So based on that, it has then the GPA has to be lower for the second one in
Mhm.
order for it to be 3.5 as well.
Perfect. Okay. So let me say, I can't pretend to mind read, but I think that there's a good kind of like, this is my guess, is that you all thought that this person should have the higher GPA because he had the higher ACT score. So this guy has a 20 on his ACT score, and you kind of thought logically it makes sense that he has a lower GPA. And this guy has a higher ACT score, so we think he should have a higher GPA. But here's the trick: is that in order to have the same predicted college GPA, the person with the higher ACT score needs to actually have a lower high school GPA, and the person with the lower ACT score needs to have a higher GPA. So this is like a really interesting thing. Actually, let's just do the math really quick before I get carried away, which I'm prone to do. So we'll do the math really quick here. So just so we know, the right answer was this one. So we're going to 0.05 times 20 is 1. 0.05 times 25 is equal to 1.25. So we're going to take off this and this, and we're going to subtract 1 here. So this will be 2. This will be 1.75. No, wait, is that wrong? Nope, that's right. And then that is equal to 0.5 high school equals 0.5 high school. So this guy's high school GPA, I might have done something wrong, but I get 4. And this guy's high school GPA, I get 3.5. Okay, I might have done that wrong. Let me just check it. .5. I did something wrong. Let me see here. Oh. Okay, no, I was right, sorry. So we get that this guy's high school GPA was 4, and this school's high school GPA was 3.5. So this is a really common thing that people find. This relates to a really common thing that people find is that within a college, so say I just took UC Merced students and I regressed their college GPA on their SAT scores. I would tend to find, actually, let me do a different example first, okay? Say that I look at linemen. I'm not a big sports person actually, but linemen is a great example. So here is their weight. And we could just like measure how many stops they make, how many times they stop an opposing lineman or something. What we actually find is, and so it's like obviously thought that a bigger lineman will be better. They can keep the other guys at bay. They would, that being big is an advantage. So when you plot the data and you measure how well they do on their weight, you actually find this funny pattern like this. Okay. So if we drew a line through this, what we'd say is, oh, look, there's no relationship between a lineman's weight and how well they do on the field. And that's funny because like, you know, that if you put me on the field, I would get crushed in like 2 seconds. Okay. So what's going on here? What's going on here is that the people that are very light, smaller linemen have something else going on. They're really strong. They're super fierce. They have some sort of X factor that allows them to compete with people that are much bigger than them. And the huge linemen, they might be good, but they I guess they have other things that are maybe weaker about them. So it turns out that there's this kind of big flat relationship between weight or size and how good you are as a lineman. And if you look within a school, you'll find a similar pattern where instead of weight, we have SAT scores or something like that. And instead of stops, we have like your college GPA. Okay, so we tend to get a pretty flat relationship between SAT scores and college GPA within a school. And so this was like a famous kind of mistake that Boston College made a couple of years ago. They said, we're going to get rid of the GRE. I can't remember if it was the GRE or the SAT, because there's not a very strong relationship between the SAT score of people we admit and the college GPA of people we admit. But the fact is that the people that had low SAT scores and still got into Boston College, they had really high GPAs, but low test scores. The people that had really high SAT scores and got into Boston College, but didn't go to somewhere better, had really low GPA, had a really low high school GPA. Okay. So what that means is just when someone has something really great about them and they're all getting into the same place, or something has someone really negative about them and they're all getting in the same place, they have other things that you're not looking at that explain the differences and the fact that they're all performing at about the same level. That's just a really kind of an interesting phenomenon. So if you meet someone and they had a really high SAT score and they're at UC Merced, it is likely the case they had a really low something else. If you find someone with a really low SAT score at UC Merced, it's likely the case they have a really high something else. Okay, any questions? Is that interesting? I don't know. Okay, so let's see. Let's take a short break, and I will be right back. Feel free to take a bathroom break or get some water, and we'll be right back.